So in this video we're going to go over how to identify when vectors are parallel. And so the idea is if we have vectors u and v, that the two vectors are parallel to each other if we can find a scalar c, so that c times u equals v. And kind of in a picture, what we're saying is that, hey, if we have a vector u and a vector v, if they're parallel to each other, or in other words have the same slope through space, then we should be able to find a scalar that either shrinks u down to the size of v, or if v is parallel but larger, there should be a scalar that scales u up to be the same length as v. And so that's all this definition is saying. Hey, if you can stretch or compress a vector, or even reflect a vector, so that the two vectors are now exactly equal to each other, then they have to be parallel. So we can use that idea to determine whether we have parallel vectors or not. So for example, we can look at the vector -6, -4, and 10. And if it's parallel to the vector 3, 2, -5, we should be able to find a scalar c so that we can either stretch, compress, reflect. We can make some scalar modification to the vector 3, 2, -5, so that it's equal to the vector -2, -4, 10. In other words, -6, -4, 10 should equal, if we distribute our scalar into the parentheses, 3 times c, 2 times c, -5 times c. And so you can see if we just grab the x components and do this mechanically, we can see that -6 should equal 3 times c, which means -2 should be equal to c. And then you need to check and make sure that -2 works with the other components. So we plug -2 in everywhere. -2 times 2 is -4, that matches here. And -2 times -5 is 10, which matches here. So we can conclude that this vector is parallel to our vector v. So in A, for A, they're parallel. For B, we would need to find, for the vector 2, 4/3, -10/3, we're still looking to see, is there a scalar c, so that when I multiply it by the vector 3, 2, -5, the vectors are exactly the same. And so notice that's going to mean that 2 is going to need to equal 3 times c. And if we solve this, we see that 2/3 would need to equal c. And so the question is, if I multiply 2/3 times the other two vector components, will I get the same components I have here? So is 2/3 times 2 4/3? Yes, it is. So it works there. Is 2/3 times -5 -10/3? Yes, it is. -5 times 2 is -10/3. So in the case B, they are parallel. So finally, for C, we need to find, for the vector 6, 4, 10, we need to find out if there's a scalar c such that this equals c times 3, 2, -5. So we play the same game. We know that 6 is going to need to equal 3 times c. This means that 2 needs to equal c. But then we need to check and make sure it works for all of the other components. So does 2 times 2 equal 4? Yes, it does. Does 2 times -5 equal 10? No. 2 times -5 equals -10, which does not equal 10. So no value of c equals, so that we can scale this vector to be the same as this vector. So this one is not parallel because no such c exists. In other words, if we're really trying to draw the conclusion, we could say something like this. We could say, note that 6 needs to equal 3c, which implies c equals 2, and -5 times c needs to equal 10, which implies what? That c needs to equal -2. But c can't equal 2 and -2 at the same time, so therefore they're not parallel. That's horrible. Not parallel. There we go. That takes the spelling out of it.